Hello everyone, let's continue. In the last couple of videos, we discussed about the MOSFET behavior in the saturation region. By saturation region, we meant that when we increase the VDS voltage to such an extent that your VGS minus VDS just goes below VT, it just goes below threshold, and the channel begins to disappear over here. So few contradicting things happen over here. So initially when we were in the linear region, we had this channel voltage as VGS minus VDS. Okay, and during the pinch off region, you have the same channel voltage going less than VT. So what does that actually mean? So these are two contradicting statements. During this area, when the channel voltage was VGS minus VDS, your transistor was working fine. You had some valid channel available. But now same channel voltage, when it goes below threshold voltage, you don't have the channel available. And what you have now, it's this small channel that is beneath the gate. So that's what is available to you now. So in the saturation region, the channel voltage just changes. It's basically remains constant, and it's VGS minus VT. And why is that so? Because now you have a valid channel, an available small channel to you, who's not dependent on the VDS voltage, because VGS minus VDS has crossed all its limits and it has gone below VT, and you see the channel getting disappeared. So in the saturation region, your channel voltage almost remains constant, in contrast to what we saw in the linear region. It was a function of VDS. So in this case, your voltage across the channel remains constant, and that's the good part in the saturation region, because we don't have a dependency on VDS. We have a dependency on VDS, but not to that extent. I'll come to that point. Basically, the channel length, this is now your effective channel length. If this was your complete gate effective gate length, this is your effective channel length, and the channel length is still being over modulated. It still gets modulated by the application of VDS, and there is a factor, there's a channel length modulation factor that can be put into the equation, and the equation becomes complete. But for now, from a top point of view, you see it's no more a function of VDS. So that's the good part. We have to handle very few variables over here in the saturation region, and the variable that we have to handle over here is VGS minus VT. Okay, so with this in mind, with having the channel voltage, taking this value of channel voltage and plugging into our current equation, let's see what do we get. So let's do some amount of derivations over here. Okay, so what we have is, we had this one. So we did some amount of derivation where your drain current was a linear function of VDS. So we removed VDS square by 2, because assuming that at lower voltages of VDS, this term just vanishes off. So we remove this term, and it comes to a point where your drain current was a function of VGS, or a drain current becomes a linear function of VDS. Okay, but when you move to higher values of VDS, we identified that the channel voltage remains constant. So when we say the channel voltage remains constant, or the overall area voltage remains constant. It's about VGS minus VT. Okay, and once VDS extremely high, where VGS minus VDS goes less than VT, this term is no more valid. So what we'll do, we'll replace this we'll replace this by a new condition, where you have the drain to source voltage. So when we say channel voltage, it's basically drain to source, the voltage between your drain to source. That's your channel voltage. So VDS will replace VDS by VGS minus VT. Okay, and then try to solve this equation. Why did we do so? Because it's very simple. When we say VDS, it's drain to source. Drain to source is nothing but your channel. It's your channel voltage, and the channel voltage remains constant when this condition VGS minus VDS just gets below VT. Okay, so this gets replaced by the channel voltage gets replaced by VGS minus VT, and over here the VDS will now be replaced by VGS minus VT, and sets your new channel voltage. And let's do that, and we'll identify the drain current equation in the saturation region. Okay, so it becomes very simple to solve. So it just like VGS minus VT, it becomes ID equal to Kn by 2 VGS minus VT the whole square. So it's no more a linear function of VDS. That's what the point we need to prove. So it's all constant. So for example, your threshold voltage is constant. If you keep your gate to source voltage at some constant value, and you increase your VDS to such an extent, to such a very high value, this acts as a constant current. So the current remains constant at whenever you move to a condition when VGS minus VDS becomes less than VT, or when VDS goes at higher values of VDS, your drain current just becomes constant. And that's what the curve that we are going to draw, or we are going to simulate using SPICE. we'll come to spice derivation or the spice simulation for this particular current equation. Okay, so it's no more a function of the no more a linear function of VDS, and that's the good thing because we now have a very few variables to handle. We have only VGS, we have only VT. Okay, so it's always, it looks like this thing acts as a constant current source, but that's not true. I'll prove it in some time from now. So let's try to summarize everything what we said till now. You have this drain current, you have the Kn was your process trans conductance, and this was the complete equation of Kn. So we replaced Kn by Kn dash W by L. So this is how it looks like. So from this equation, it looks like the drain, as and when you reduce your channel length, your drain current increases. But that's again not true. I'll come to that point as well, that what happens when you go to lower channel lengths. It basically the inverse behavior that you see, and the reason for that is velocity saturation. We'll talk about velocity saturation in some time from now. Once we prove that whenever you reduce your channel length, your drain current reduces. So we'll first prove that, and we'll try to understand why it happens, and the reason is velocity saturation. I'll come back to that point whenever we do a spice simulation for lower nodes. So we'll be doing a spice simulation for higher nodes, and a spice simulation for lower nodes using the same technology model file, and see what happens. And that's where you will come to there will be an observation that we'll be seeing, that your drain current just reduces when your channel length reduces. So this equation no more holds valid. We'll prove that in some time from now. Okay, so looking in this equation, it looks like your drain current is a function of all constants, provided your VGS, we have kept, let's say we have kept the VGS as 1 volt. So your drain current looks to be a function of all the constants. Okay, so it looks to be a perfect current source. So constant current, you can use a MOSFET in this condition and use it as a constant current source. But somewhere that's not true, and we'll show you why. So basically, if you see the channel length, if you see the effective channel length over here, this is not your effective channel length, but as and when you increase your VDS even beyond limits, this effective channel length reduces. So basically, it gets modulated by the amount of VDS that you increase. Okay, so it's still not constant, that the drain current increases a bit whenever you increase your VDS. So it's a minor linear function of VDS, and basically when you increase your VDS, your depletion region near the drain increases, and your pinch off area again increases. So effective channel length decreases. So as a result of that, it's not completely independent of the variable VDS, but we have some dependency on the VDS, and let's try to give a name to that. So now here we have seen that whenever you tune your VDS, your channel length gets tuned. So let's give it a name. Let's call it as a channel length modulation factor, and call it as 1 plus lambda s. So we'll take this complete equation and multiply it by 1 plus lambda VDS, and this will be trying to prove in a separate set of videos, will be where we'll be looking only into physics equations. So let's keep this thing for now, but we'll add this term towards the drain current in the drain current equation, showing that it's not completely independent of VDS. Whenever you increase your VDS, you still tend to see some behavioral changes. So drain current is not constant, but slightly increases when you increase your VDS, and we'll show that when we do the spice simulation. And now this particular equation becomes your constant current equation for the saturation region of MOSFET. So we came up with a threshold equation in the beginning, then we started with the then we came up with the drain current equation for the MOSFET in the linear region, and now this is where we have the drain current equation for this MOSFET in the saturation region. So we will use these three different models and try to do this spice simulation. So that's where it introduces us to now this is the right time to introduce you to spice. So what we'll do, we'll cover this as a separate section, as a separate complete lecture. So since I'm already running out of time, in the next video let me try to introduce you to spice, and let's bring up what all the parameters needed. We'll first build the spice setup, and then we'll run spice on this particular MOSFET at two different technology nodes. Okay, so let's try to do all those, and let me try to introduce you to spice in the next video. Thank you.